Thank you everybody for coming to the very first official Stars on Tap event. So for those of you who do not know, STARS stands for South Texas Astronomical Society, and it is my project with Maki here. And for the better part of this year, we've been working with the university and with Dr. Diaz, he's over there. His group, the Center for Gravitational Wave Astronomy and the Cristina Torres Memorial Observatory. Most of them are over here, all great people. And so we've been working with them for the better part of this year to throw lots of different types of events and stargazing and events at the library, and it's been a great time. And we've been wanting to do this for a while, have an event where we can get together and drink and have a good time and talk about something cool. So we're going to try to do themes for these events. And so the theme for this Stars on Tap is extraterrestrial life. And so our presenters are going to talk today about evidence that at one point people thought was evidence for extraterrestrial life. And so without further ado, the first presenter is Richard Camuccio. He's right here.
See that okay? So I have some notes here for tonight. Thank you all for coming. This is actually really exciting for me because this is something we've talked about for many years, and I never thought I'd see it actually happen. So it's kind of surreal being up on stage and talking to you all, but I'm happy that we had this opportunity, and I want to thank all the hard work, Maki and Victor and all the other people that are here supporting us, all of you for supporting us. So thank you for coming and making this real. Today, I'm going to be talking about what I would consider to be the biggest question in science. This is my opinion, and it's simple. It's where are they? They being other life forms, not just us. We know that life exists because we're here, but that's not enough. We are interested to know if we're alone, if we have good company or bad company, and how many there are. So I say solutions to the Fermi Paradox and quantifying extraterrestrial civilizations. What I mean by these two things I'll explain, but basically we're going to try to figure out how to answer that question, and then in the next two presentations we're going to see some particular cases of trying to find the answer. So this is more of a theoretical background, but I hope it sparks some good discussion. And the other thing is, if there's like questions, you can ask during the talk. I don't care. Like you don't have to wait until afterwards. So if there's something prevalent, I like this to be more of a conversation anyway. So, all right. So a little overview of the talk. It's going to go by, I got about 20 minutes to go through these things. I'm going to define what the Fermi Paradox is if you haven't heard of it before. It's a pretty simple idea, but we'll have to first define it so we understand it. Then we're going to see how to solve it. And there's a couple of ways to solve it. There's actually many ways, but we're going to talk about two in particular. What we want is a solution of the form, how many civilizations are there out there maybe, or intelligent species, or just life in general. Where and when are they, and how advanced are they? It's not easy to answer these questions when there's only one case of it, which is us. It's like working with one data point. So answering these questions you're going to see is actually quite hard, and I'm going to hopefully demonstrate that using two calculations and then offering several hypotheses on why we actually don't see anything right now. And there's a lot, so we'll go into that. So the Fermi Paradox is very simple. It's the question, where are they? Science tells us that we should be in good company with a lot of a plethora of different types of life. Astrobiology has shown us that the chemicals for life are everywhere. Even on Earth, extremophiles have showed us that you can have life in places that we wouldn't survive ourselves. So you can have very crazy situations where life somehow survives, that life finds a way. So the question of the Fermi Paradox first came from Enrico Fermi in the 1950s. Apparently it was over lunch when he was at Los Alamos studying nuclear physics with his colleagues. And at one point, he just randomly asked the question. It was at lunch. He said, "Where are they?" And they all knew what he meant at the time. So it became historical right there in that moment, and it became associated with him. Even though we'd asked this for thousands of years, it was formalized really by Enrico Fermi about 60 years ago. And on the right side, I put this. Who has seen this before? I'm just out of curiosity. The thing on the right. Okay. This is our proverbial message in the bottle that we put into the cosmic ocean. It's the first one we ever sent. This is a visual representation of a radio signal that we broadcast to the galaxy M13, which is 25,000 light years away. So it'll take this signal 25,000 years to get there. This was sent in 1974 by Carl Sagan and his colleagues, and it's our first attempt to actually communicate with other people. This is the first transmission we deliberately sent out in order to say, hey, we're here, and this is what we're about, right? This should be decoded by an intelligent species, but each of these, and to me it's not obvious, some of these things, like I didn't know what these things were, and this is supposed to reflect us. So you can imagine that if we get a signal from an extraterrestrial civilization, it's not going to be obvious at all. But in this case, I kind of wrote what these things mean. We're explaining that we have a numerical system, base 10. We count with 10 fingers, that's where it came from. The atomic numbers for hydrogen, carbon, nitrogen, oxygen, phosphorus, which are the base elements of life on this planet. The sugars and bases in the nucleotides, which builds the DNA structure here. And this is actually a representation of the DNA double helix, so it's to explain to aliens, hey, we're made of carbon, our DNA looks like this is how we express our proteins and how we evolve. Here's kind of a human representation, anatomical human being. These lines over here represent the average human dimension, so height and weight. And then over here tells you the human population. So at the time, it was a lot less than it is now. I think it's well over 1 billion more people on Earth since this message was sent in the 1970s. The solar system, Earth being highlighted as the originator of this message, and then the Arecibo telescope, which sent the message, and it kind of gives an idea of the technology that we use to send these types of things. So this is something that presumably someone might pick up, probably not, but it was our first deliberate attempt, and so that's why I put it on here. So these are the first two major steps for the search for extraterrestrial intelligence. So now I'm going to talk about two specific ways to quantify how many civilizations are there and how advanced could they be. The first would be how many are there, and that's reflected in the Drake equation. Looks like this, and this is one of only 2 cases where I'll be showing math tonight, but it's actually a very simple equation. It's just a bunch of fractions that you multiply together, and n should be the number of presently communicable civilizations in the galaxy right now that we could theoretically talk to. Now, I'll explain the complexities of this in a bit, but this was formulated in 1961 at the Green Bank Observatory in West Virginia. I don't know if anybody's ever been there, but you could play a full-size soccer game in that dish with room to spare, probably for your house. And I was up here, which is very scary for someone who's afraid of heights. This is a picture I took in the conference room. That conference room in 1961 was the first conference. 1961, it was very controversial to talk seriously, scientific discourse about extraterrestrials. So to organize this conference was non-trivial. It was a big deal at the time. And consequently, it was complex to actually come up with a scientific agenda. Nobody knew what to talk about, nobody knew how to organize this. So Frank Drake, the night before the conference, he was the conference organizer, came up with this equation to basically guide the discussion. It had nothing to do with actually trying to reflect what was reality. It was merely to guide the discussion. And so you can see him down here later in his life, 50 years later. So the Drake equation, what does it mean? Well, we'll start with the one that we know the most. These reflect different phenomena that we have to answer before we can begin to understand how many civilizations are out there. So R sub star is how often stars are formed in our galaxy, right? So if there's more stars that are forming, then there's more likely to be some of those stars that have planets, that have life. So the number of civilizations depends on how many stars are being born in the galaxy. It depends on the fraction of those stars that actually have planetary systems. Now in the 1960s, we basically knew R and nothing else. Now we know kind of these three and still nothing else. So F sub p tells you how many planets should be per star system, and we're finding that planets are actually the rule, not the exception, that every star has at least one planet. So that's cool. So that number would be 1, that's good. NE is just the number of those planets that are Earth-like. So Earth-like being terrestrial, they have their rocky surface, and they orbit sufficiently far away so that if water exists on the surface, it exists like liquid. F sub L is the fraction of those worlds that actually develop life, and we don't know what that means. F sub I is the number of cases of life where intelligence arises, and we know one case, which is us. You could make an argument for a few other species on this planet, which I would permit, but I'm just assuming that anything on Earth, we're intelligent. We know that it has arisen once, at least once in the history of the universe. It's here, could be elsewhere, but we don't know. And then an F sub C is the number of those that have communication technology that we would actually be able to hear. So we currently satisfy that, but only in the last 60 years. So the universe has been around for, what, 13 billion years? We've had this since the 1950s, basically, the 1960s. So you can imagine that to get to that point, it's pretty hard. L is the length of time over which we could communicate. So if our civilization collapses tomorrow, that is our length of time, basically. So how long? The longer your civilization exists, the more likely you'll be able to communicate with it eventually. N gives you the number of currently present civilizations in the galaxy, just our galaxy alone. So I want to ask a question to the audience, actually, because I'm going to ask 2 questions tonight. And they're both the same question, but for different contexts. Do you see any problems with this? Everything I just explained? Do you see limitations? Do you see, someone give me an idea. There's no wrong answers. I made a lot of assumptions, didn't I?
Yes.
Yeah, I made a lot of assumptions. And the problem is, the farther right you go, the less understanding we have. So we really, astrophysicists have nailed down our star since the 60s, and it's pretty much the same. But everything else is pretty much uncertain. And I demonstrated in the slide really quickly, rather than I turn it back. This is the range of values you can get. So that's 9 with 13 zeros, and that's what, 100 million. So these are the range of values, and could be depending on which numbers you put in, and all of them are valid. So there's this large unconstrained space. We're not really sure, is there 1, is there 20, is there a million? Just to give some examples, if you put a pessimistic argument in, you get that number, which basically means we're not only probably the ones in the galaxy, but we might be the only intelligent species in the entire universe, at least observable universe. So very pessimistic view. On the opposite hand, if you give more if you give better views, and particularly if you look, L, 304 years is assumed based on human civilizations, how advanced the most advanced civilizations have been. This is 1 billion, so this is assuming, hey, maybe they get their problems worked out and they come together as a species and they exist for a very long time. So there's a range of values you can have. In this case, it's about a little under 16 million presently communicable civilizations in this galaxy right now. So that's the problem that I was trying to allude to, is we don't know, because it's such a wide variety of things. Until we're able to constrain these ones over here, which basically means we have to find life first. We're working with one data point. We're never going to answer this question. So this is not really a good guiding principle, but it's interesting to think about. Okay, so that would be how many are there in the universe. But then you want to ask, okay, well, maybe there are some. How advanced do they actually get? And how do we even define advanced? I mean, you can take it from the ability to change your environment, the ability to expend energy, the ability to have lots of information and process and store information. So one of the oldest ways that was formalized was the Kardashev scale. It was invented in 1964, 3 years after the Drake equation was invented. So the 60s was a big time for SETI. That's actually when SETI, the Search for Extraterrestrial Intelligence, was founded, right after this. The Kardashev scale was invented to define how advanced a civilization is based on how much energy it could expend. Okay, so the original formulation, I don't know how many people are familiar with the Kardashev scale or have heard about it, but it's expressed as a civilization of type 1 status, type 2 status, or type 3 status. And since it's based on energy expenditure, the way that we look at it is a type 1 civilization can consume all the energy resources on its planet. That's currently not us. We're not even a type 1 civilization right now. I'll show that in a second. A type 2 civilization could access all of the energy that a star produces. So if we were able to take all the energy that comes out of our sun, not just the stuff that's coincident with Earth, but all of it, because most of it, 99.9% of it gets radiated out into space. If you can capture all of that and really use it, you'd be a type 2 civilization. And these numbers right here, all this means is that's a factor of 10 billion in power output. So you can imagine it's quite a jump to go from type 1 to type 2 to type 3. Type 3 civilization would be able to consume all the luminous output of its entire galaxy. So the case of a type 1 civilization, this is the inside of a nuclear reactor, a fusion reactor. If we were able to sustain nuclear fusion, we would quite rapidly become a type 1 civilization. We would have access to a lot of, pretty much the energy problem would go away. Type 2 civilization would be a little more exotic. Freeman Dyson in the 1960s came up with this idea of these large-scale structures. If you can consume all the energy of your star, you could do these massive astro engineering feats. So in this case, these are representations of, you have imagine your star is in the center and you build these structures around it. It could be a ring, it could be a shell, it could be a bubble of satellites. And the idea is they're collecting all that sunlight and then using it for something. But this is on a very large scale. This is bigger than the Death Star or something in sci-fi. This is huge. This is at the orbital radius of the Earth, for instance. So you can imagine that these advanced civilizations can pull these astro engineering feats. Type 3 civilization is very speculative because we're not sure if you could even coordinate over those large distances, right? To the nearest star is 4 light years. So if you had humans there and you wanted to talk to them in real time, it would take 8 years at minimum to hear back from them. You send a signal, it takes 4 years. They send a signal, assuming that they respond immediately, and it takes another 4 years to come back. And that's just the nearest star. This right here, in this scale, each dot is a galaxy. These are not stars. And this is just the nearest group of galaxies. This is not even a fraction of the cosmological distances that we know. So we don't know if a civilization could coordinate over that scale. If it could, it would be a type 3 civilization. Sci-fi analogies, type 2 civilization would be like the Federation in Star Trek. That's a classic example. Type 3 civilization would be like the Galactic Empire. They can pretty much do what they want. They can go anywhere in the galaxy. I mean, how real is that? I'm not sure, but that's the way we would scale in terms of energy. Now, again, like I asked with the Drake equation, what's the problem with this? Well, the problem is this is very anthropocentric, meaning we're used to being explorers and going out into the world and seeking the unknown and bringing back something for civilization. And we're used to building things and producing a lot of heat and energy. But maybe that's just us. Maybe life is different. Maybe that they have different motivations. We are hunter-gatherers, so we want to identify our boundary and go out and explore the unknown. That's why we're explorers by nature. So maybe that's just us. Maybe there's other types of psychologies that drive different decision-making skills. So we don't know. That's the thing. The other thing is our current state. We're not a type 1 civilization, we're a 0.73. We haven't even been able to consume all of the resources on our planet, even though we're getting pretty good at it. And we would go up by 1,000th of a decimal point, like 0.001 per year. So to get to a type 2 civilization would take thousands of years. It's very hard to get there. So we're not sure if you could survive that long and actually achieve that level of technology. A couple of other ways that you could define a civilization. This is my favorite astronomer, Carl Sagan. He's holding the plaque that was a representation of the plaque that was sent on the Voyager probe. Also, interestingly enough, this is John Lomberg, who, if you're familiar with Cosmos and any of other Carl Sagan's work, all those illustrations of the galaxies and especially in the animations of the TV series, he came up with the plaque itself. So he actually designed this plaque. Carl Sagan came up with another way. He said, well, take Kardashev's scale and extrapolate it. And really all this means is the more power that your civilization can consume, the higher your advanced, how advanced you are, basically, the more advanced you are. That's all this really means. You don't have to worry about the numbers. From this, you could define where we are. That's where I got 0.73. So we're like 3/4 of a way to a type 1 civilization. His contribution also was to add an additional factor that goes from A to Z, so alphabetically, and there's 26 of these. A represents a civilization that can have 1 million bits of information, which really is not that, it's really not a lot. The Greeks had way more than that available to them. A Z might be unattainable. That would exceed the information capacity of the entire universe. So if you were to take every atom that we know that's in the universe and incorporate it into a computer, that number would still be bigger. So we're not sure if a civilization can access that amount of information, but we're somewhere in the middle. I think in 1973 we were in H, which is 10 to the 13. I think now the total information on the internet is 10 to the 20. So we've gone a ways, but these two ways, energy, information, the two primary physical things. Physicists are concerned about energy and information. These are the two fundamental ways that you can define how advanced a civilization is. And here's just another example going from 1965 to, I think this goes to 2017. This is the world's energy consumption, primary energy consumption. So this is some sum of oil, natural gas, renewables, nuclear energy, and coal. And so over time, this has gone up. Kind of interesting to note that this is where the recession was, and there's a little dip here. I saw that. I thought that was pretty interesting. But basically, this slope, it looks like it's going up pretty fast. But if you were to correspondingly ask how advanced are we getting over this range, it's not a lot. We really haven't become that advanced over that amount of time, even though it seems like we have. Our ability to do Astro Engineering feats isn't really that impressive. So yeah, that's the two ways to quantify things. We can quantify things by how many civilizations there are, maybe where are they, and how advanced are they. Now, I'm going to get to the final part of the talk, which is addressing the Fermi Paradox directly. Since these two methods that I've just demonstrated, they're very uncertain, it begs the question, what if we keep looking and looking and looking and looking and we just don't find anything? It's a term that I like to define as the great silence, right? Science tells us that we should have lots of life in the universe, but we see nothing. Sure, we just started our search, but this is the big problem. This is the Fermi Paradox. And so the question is, so where are they? I'm going to offer 5 categories of possible solutions. And I say categories deliberately because when I searched solutions to the Fermi Paradox, just a Wikipedia entry gave me 23 solutions. That was just on Wikipedia. And I knew more, and there's other ones. So what I tried to do was take all of these 23 plus solutions and put them into kind of a 5-part category. I hope I did a good job with it. But the Rarity Hypothesis, the hypothesis of the great filter, physical limitations, what I call the fad of the galaxy, or what's in vogue, and I'll explain what that means in a bit, and then ignorance, and that's our ignorance. Okay. So the Rarity Hypothesis is the first one. This one's taken from Carl Sagan's Cosmos. I don't know if anybody's familiar with this, but this was his fantastic view, illustrated view of what it would be like to exist at the level of the atmosphere of Jupiter where it's warm enough where we could actually survive comfortably. This is what it would look like. There would be scattering just like us, but you can see these columns of really strong. Like if you were to go into that, you can see vortices here. These hurricanes are bigger than the Earth. So the scale is a lot. It's harder to see just from the picture, but the other fantastic thing I wanted to point out was these bubble creatures. He hypothesized that life could, he was very optimistic about where life could exist, and he thought, well, maybe there's hydrogen gas and there's proteins floating around in the atmosphere. Maybe over time they came together and formed these bubble creatures, kind of like they're underwater, but it's in the atmosphere. But the point I'm trying to make here is that maybe life is rare, maybe it's not as easy to create these fantastic ideas, as sad as that sounds. Maybe life is rare or non-existent. Maybe we could be the first. Maybe there will be more. We could also be the most advanced. I'm thinking like the Ewoks or some primitive but intelligent species. Yeah, Star Wars, I think, right? I think next month we're going to do Star Wars. Right? Is that yeah. They could be intelligent, but they might not just have the tools to communicate with us. Or we don't understand what consciousness is, and maybe it's a really special thing. That could also be. Or there's other ones. There's what I call the great filter. Does anybody know where this is? Does anybody know this crater? Meteor crater. Meteor crater, yes. This to scale is 1 kilometer long. and those are house-sized structures. I've been right here on this ridge looking across from it, and it's unreal. You have to go. This was produced by an asteroid that could fit comfortably on this stage. I could probably give it a hug. It's not that big, but it produced a crater that size. My point for showing this is that maybe there are great filters in nature as civilizations advance. They run into these just natural disasters that prevent further advancement. So we've exhibited 6 mass extinction events on our record. We somehow are still here, but there were plenty of attempts in the past to eradicate life on Earth all natural and unexplained, a lot of them unexplained. So stuff like this is a very small example of what could be considered a type of great filter. Maybe your planet gets bombarded too often, or maybe you're near a very highly unstable star that puts out a lot of radiation and just sterilizes the surface of the planet. These types of things could happen. Maybe it's the nature of intelligence to destroy itself. And that's something for someone like me who was born after the Cold War, I probably don't appreciate as much, right? We came very close to killing ourselves many times. That's something that motivated Carl Sagan to come up with these ideas as well. So maybe it's the nature of intelligence to destroy itself or to destroy others, which has been exhibited throughout thousands of years of human civilization. And then I said periodic extinction. Another one would be physical limitations. So as a physicist, I'm most interested in these types of things. There's the water world hypothesis, like we have the case of the whales and the dolphins. I would consider them intelligent, but they don't have thumbs, and they can't interact with their environment as intricately as we can, so they can't construct tools. They have a much more elaborate language than us, like a 20-minute long song, it contains much more information than we could possibly unravel. Yet they can't communicate with the outside, with outer space. So maybe there's these types of exotic environments where they're intelligent, but they can't actually communicate with us. Maybe they're too far separated. Maybe civilizations just don't arise that often, but when they do, they're so far away that, like, 500 light years from here is Betelgeuse. If you were to be on Betelgeuse right now and look at Earth, you would see, what, the 1500s? So it wouldn't be now to us if you were even only 500 light years away. And I say only 500 light years because that's still within our galaxy. If you're an extragalactic civilization billions of light years away looking, there would be no way you could detect intelligent signs from that distance. Could be lack of resources, and it could be that planetary migration is very difficult, which it is. So maybe there's better ways to get advanced rather than going out there and colonizing things. This is supposed to be a supermassive black hole. It's not really that accurate, but it'll do for this. Basically, I put a black hole here because there's the fad category. What is in vogue in the galaxy? What do I mean by that? Maybe that exploration is just not fashionable. Maybe exploration is too time and resource intensive. I mean, it is for us, but maybe on these larger scales, it becomes exceedingly so. So maybe exploration via remotes, maybe sending little nano-sized robots to explore as many different star systems as you can and just beam back information, build a picture of the universe without actually having to get off of your couch. Maybe everyone listens and no one speaks. That could be something. Or colonization is a very human/explorer idea. That's something that I alluded to before. Maybe we think that everybody's just going to go out and try to explore, but that could just be us as hunter-gatherers. And the other one is they tend toward isolation. This is something that I think is more likely than all the other ones because we're seeing this right now. Everybody is absorbed in their phones and virtual reality is becoming a thing. What if you can create a perfect replication of the world, but with all the possibilities that you ever wanted? People would go into that rather than explore the universe, especially if it's energy intensive, right? And we see that happening now. So maybe civilizations just tend towards a virtual environment and then they just exist in this perfect state for as long as they want, really. That could also be. That's why maybe nobody's talking. And the last category, oh yeah, they're sleeping. They could be sleeping. Okay, so I surprised myself that way I'm talking. When you get very close to a black hole, to you, time ticks just fine. But to someone else, it's much different. So if I wanted to basically live a very long time, let's say billions of years, all I have to do is get really close to a black hole. Not inside it, just really close to it. And I wait. And I could wait a few minutes. And then when I step away, the universe billions of years have passed. That's real. That is a real physical thing. So maybe, and there was a paper a couple of years ago that really excited me when I read it, that suggested maybe aliens are in hibernation. And the idea was we're still cooling from the Big Bang even now. So maybe it's too hot. Maybe it's energy inefficient. Maybe if you hibernate and you wait eons, trillions of years until the universe cools, and you wake up, your ability to compute and your ability to actually do things dramatically increases. And I mean times 10 to 50 zeros, and this was in the paper. You could actually maximize your computational efficiency by just sleeping and waiting until the end game. It's like the game of strategy. Don't win the tactical. It doesn't matter if you lose or win in the tactics, it's the long game. You want the strategy. So in this case, if your strategy is longevity, it's best to wait, sleep, have all those humans burn all of their stuff and kill themselves off, and then when the universe is cool, we can wake up and actually do a lot more than what they thought they could do. And the last category, I mean, this is one of my favorite pictures from John Lomberg. The last category is ignorance, and this is something that's probably equally plausible to the virtual environment thing I was talking about. Maybe they are just too alien, and we just don't recognize them. Arthur C. Clarke said that sufficiently advanced technology is indistinguishable from magic. I believe that, right? That's something that could be. Maybe we're deliberately isolated. That's also known as the zoo hypothesis. The zoo hypothesis solves the Fermi Paradox by saying, hey, maybe we're just too warlike, we're not ready to go out there and interact with these higher intelligences. Maybe we're missing the point where we're too busy killing ourselves, where we're not ready to interact with other species yet. We can't get along. Or maybe they have been here, or they are here, and they're just unnoticed. I mean, that's not out of the realm of science, and I don't hesitate to even say that, because I know people see things, and that should be taken seriously, but at the same time with a healthy dose of skepticism. And the last two, which I really like, are we aren't listening properly. Maybe we think radio is the way to go, and that's just so primitive. It's like trying to communicate with a carrier pigeon. We haven't existed long enough. We've had radio technology for less than 100 years. We barely scratched the surface of the moon. The universe has been around for 13 billion years. The galaxy has been around for 10 billion years, so the galaxy was along way before Earth. 6 billion years before Earth, the galaxy was already formed. There could have been civilizations that were like tired of it and just left, or who knows. But maybe we're just, we haven't existed long enough to really begin to search. And with that, I would say, because, yeah, that's basically it. After all, as Life Horizon, we basically woke up just yesterday in the scheme of things. And I think that picture artistically represents that, and I'll leave it at that. So thank you for your time. I think we have 15 minutes, so we could talk if we want. If there's any questions or. I hope I didn't cause any existential crises. Oh, no questions?
You were wonderful.
I think you had a question.
Yeah, no. I don't know if you're aware, have you heard of the Advanced Aerospace Threat Identification Program?
Not specifically, no.
Okay, that's something that's kind of interesting about that is, I've been, like you, I have a passion for this. I've been studying this for a long time. One of the biggest problems is there seems to be like a massive dichotomy between government work and universities, and they're just not crossing over. I'm pretty convinced if you take a look at Atip, which was actually funded by Harry Reid, the leader of this at the Pentagon was a guy named Lou Elizondo. I'm pretty sure that if you look at, and if you study this is not pseudoscience, this has been out in the public, it's been out for years now, I think it's about 2 or 3 years it's been out, that the United States government, I don't think it's about the last 10 years, has been studying what they call unidentified aerial phenomena. They released 3 videos that this individual actually says that, look, we have the videos, they've been released. If you look at it online. You guys can all see them on YouTube. One of them's called Gimbal Fast Rider, and another one, I can't remember what it's called, where it shows objects through forward-looking infrared from F-18 Hornets that are doing things that we just cannot do. There's a group called To the Stars Academy that's comprised of the head of Atip, or the former head of Atip, former deputy secretary of defense personnel, all these kinds of people that are saying, look, this stuff is real. It is extremely likely that this is not from this planet and that there is no explanation. So, I mean, that's something to look into, maybe just a little bit. I know that Senator Harry Reid also did contracting work with aerospace engineer Robert Bigelow. They were talking about how the government has, all kinds of metamaterials that they don't really understand how Bigelow Aerospace was able to develop these so quickly. It all ties in there. So, I mean, again, I just wish that universities would maybe, get a little bit more connected with the government. But that's stuff that, is definitely legit. It's fascinating.
Yeah, and I didn't want to rule out eyewitness things. I mean, that's like first and foremost, we use our eyes, and you see something and you see it, then that should be something taken into consideration. I mean, I'm a scientist and skeptical both ways. I'm not going to believe you immediately, but I'm also going to be like, okay, we should maybe figure this out, get to the truth.
Sure.
I was going to say something also in response, but I forget. So, yeah, I mean, I'm sure people have seen so many unexplained things before, not just with UFOs, with just things in your life, and that's not something to just disregard.
Sure.
So I would agree with you there. Yeah. Just got more questions than that. You got one?
Yeah, I have one.
Yeah.
What about your opinion about the manipulation of that information? That is not ignorance, but it's manipulation.
Like in who's doing the
The
manipulating?
government.
Oh, I mean. I think so, maybe. I mean, could be. Like, that's been in the past for other reasons, not just aliens, but there's been meddling of information. So I would say I wouldn't rule it out. One of the principles I go with when I try to interact with people is never assume malicious intent. So I go off of that as a working basis, but eventually maybe if that all gets ruled out, then the only explanation left is maybe people are hiding it. And there have been things that people, I mean, I don't want to necessarily say conspiracy theories, but these ideas that there have been plenty of contact in the past, and the government was the liaison, and they didn't want the public for fear of mass panic, for instance. That could very well be, but I still, maybe I'm idealistic or optimistic. I'd like to believe that if that happened, there would be a much more honest discourse. That's just me though. Could happen, it could be. It could be meddling of information, that's for sure. It's been exhibited in the past many times.
I kind of have a question, but it's not. I just didn't understand. What? Can you elaborate more on type 1?
Type 1?
Yeah. Let's
Sure. Like.
I didn't understand how do you mean like. So when you talked about the Earth, we are not type 1 because we can't do what exactly?
We can't access all the available resources as much as it seems like we're completely desolating the Earth, which we are in a lot of cases. We're not accessing everything possible.
But what parts are we not accessing?
What's that?
What parts are we not accessing?
How about the core of the Earth, which is pretty much the #1 source of heat, the cause of all volcanism, which is the largest energy scale events on the Earth, are giant volcanic explosions.
But is that
We cannot control that
Yeah.
at all. A Type 1 civilization can control the weather, and they can control their geomagnetic dynamo.
But is that even possible?
Sure, physically it is, but you would need the scale and the technology to do it, and we don't have that. It's not possible for us. We can tap it just a little bit and extract from
I
it.
think you said like 3/4.
Yeah, we're 0.73 if you calculate it on that scale. But
But wouldn't you say that the core is such a big amount of energy that we would consider to be like way lower than that?
was that?
How's it calculated? That 3/4. If the
agree. If you could tap it all, then you would exceed a type 1 civilization, but we cannot tap it. What I mean by that is you would be able to control it. And we cannot control volcanoes. It's the most terrifying thing. Aside from an asteroid impact, it's one of the most violent and uncontrollable events in all of nature. Type 1 civilization would just be able to take that energy right out. And, oh, there's going to be a super volcano? Take all that energy and use it to build things. It would be easy. It doesn't take much in advancement to rapidly run away from us. Someone who's just around the corner in advancement would far exceed us. You might have heard of this thing where if an alien civilization were to come here, but it's always right around the corner. Just for the people that are really interested in the math, the reason why this goes up as a logarithm is because for every small increment of power, you get a really small increment in Kardashev. So like I was saying, this seems like we're getting a lot done, but in terms of the quantitative measure of how advanced you are, it's not at all. This is like basically a flat line. I mean, I've done the calculation myself. I've put this data into that equation. It would take us until like 10,000 AD to get to a type 1 civilization at present rate, unless we had a massive breakthrough of technology, which is unforeseeable, which is something I can't comment on, because you could, 10 years from now, we have nuclear fusion, that's unforeseeable. We're immediately a type 1 civilization, great. So, but that's unforeseeable, so at present rate, it would take forever, basically. Yeah.
I think you're being optimistic by saying we're 3/4 of a way there. It's not even that.
Yeah, I mean, there's probably so many issues ahead of us that we don't even
Yeah,
know.
because I mean, he's arguing the other way, but we're really not even 3/4 of a way there. Not talking about nuclear fusion stuff. We just came back from Comic-Con in Dallas. In Dallas, and there was an engineer there. I forgot the name of the guy, but he was telling us that there's actually at the University of Texas, Austin, they've been able to achieve fusion and fission in a way that they can now have the ability to spend out radioactive rods and use nuclear waste to create electricity and power. And he was saying that it's the technology is already here. It's just a matter of how they can introduce it to the people.
Yes, that's exactly correct. And actually, contrary to popular conception, we have achieved nuclear fusion just temporarily. Like this, and the other mechanism, which is to shoot a laser at a hydrogen pellet and make it all fuse at once. That can happen, and we've done it many times. It's just we can't make it a sustainable thing. And then how would you distribute that? So you would have to. Our entire economy is based on fossil fuels, so you would have to completely redo the infrastructure, the energy infrastructure.
Well, can you imagine the pushback from the future fossil fuel companies to prevent something like that happening?
I mean, I ignored one factor, which is anthropocentric as far as I know, which is politics, economics. These are human ideas.
And you're forgetting another thing is also religion.
Yeah.
Can you imagine the effect that an alien civilization will have on religion?
Yeah. So there's I guess in this talk I was trying to imagine the least human view of things, but you are entirely correct. If you were to introduce these complications, this is simple in presentation, but you incorporate sociology, psychology, all of our problems, our politics, our economies, our religions, all of these things would make this, I mean, your advancement wouldn't be as linear. There's going to be setbacks, which we've seen before, right? So.
Because I was watching a documentary on the deciphering the tablets of the Sumerian tablets, and there's a book in the Sumerian tablets that's called the Book of Neki. And the Book of Neki basically it goes into the detail of how the universe was formed, exactly how the human race was formed. It's very interesting. You can watch it on YouTube. It's called the Book of Neki. And there's also Sumerian tablets that explain also the process of the creation of the solar system and how the planets came about to be. It's very hard to follow because they use very strange names to each different planet. So it gets very confusing after a while, but also instead of also just looking into the future to be able to come up with this, with an idea. Sometimes it's in the past, it's already written, it's been written, it's just that we don't understand it.
Yeah, and I think to that point, I'll say that I think these ideas have existed longer than the written word, and they weren't expressed the way that we're familiar. We're familiar with articulation. If you have an idea, it's not well formulated until it's articulated. But that idea has not existed for a very long time. Humans have existed way longer than even speech. So I think to go back and interpret these ideas, I think it's a mistake to look at them as, oh, these were primitive people, they had no idea what they were talking about. I think that's a terrible mistake. I think they were as smart as us, they just were not used to expressing things the way they were expressed. They didn't have books, they didn't have the written word then.
That's why sending out radio wave signals to try to communicate with somebody is not just.
Yeah, it's the way we're doing it it's probably.
It might not be the way to get a response. Because it might be too, it's like you said, it might be too old of a system.
It's too energy intensive, frankly, it's probably primitive.
So yeah, you're talking about who's listening. Do they have the right ears to listen to the signals that you're sending?
Yeah.
So.
These are some good ideas. How much time do we have? Oh, we're done. I'm getting kicked off. All right. Thank you so much.
Thank you, that was great. All right, thank you guys. Our next talk is going to be from Yelbir, and his presentation is Searching for Signs of Life on Exoplanets. And that is going to be happening in about 10-15 minutes, so stick around for that. Thank you.
And I was like, that's weird. It's like,
purpose of life is to question me, but I love him for the question. Go ahead.
So you have entropy, right? And you said that everything goes dark.
Yeah.
Does it mean like our planet is gonna die really soon?
Okay. Does it mean that our planet is going to die real soon? Well, if it's going to die real soon, it's going to be us, not the entropy. Don't look for excuses. But okay, I mean, to be serious, the statement that a closed or isolated system goes to the most disorderly state, does not include any estimates of time, actually. So it could take forever, like by thousands of years, millions of years. It really depends on a particular system. So there is no built-in time scale. That depends on particular details. So,
Can I add a point to that? That might be, it's also a statistical statement. So it's not like it will tend towards disorder, it's just most likely going to tend towards disorder.
oh, well, I mean, that's true, but don't forget that it's, we're talking about overwhelming likelihood. It's just crazy more likely. And those numbers are so overwhelming that you're basically sure that it will go this way. Although some people, I think, forgot his name, but there was a famous sci-fi novel written by a Russian guy, which is called the fluctuation, statistical fluctuation, in which, because it's statistical in nature, there's this one day in the life of the universe when entropy reversed and something went in the opposite direction. So a glass basically collected, a broken glass turned into a full glass. So, but it's sci-fi. In reality, if you actually try to calculate the probability of that, it's absolutely negligible. So, yeah.
On the same question, so what do you think? So everything about the heat, right? I missed that. What was it about that? So we have planets, right, or stars, and they give out heat. Does it mean that eventually there will be no more heat in the universe?
Well, it will become homogeneous. That's my understanding. But the problem with the heat death of the universe is that no one knows if it's a closed system. The second law only applies to closed systems, to isolated systems. Is there something outside of the universe? And apart from that, you cannot apply the second law to universe as a whole because of gravitational fields. There is a theorem, I read about it in Landau's book a long time ago. Basically, someone has shown that it fails. You simply cannot make this claim that the whole universe will have a heat death. The whole thing is actually just wrong. Gravitational fields change, and they lead to, if I'm not mistaken, they lead to the whole universe in its phase space or configuration space moving towards. It changes the equilibrium state, basically. So it's not trivial to say, hey, we can apply the second law to the whole universe. You cannot.
As far as discovering or trying to detect exoplanets or trying to create some kind of theory that they do exist. Now, well, why aren't we trying to detect life elements like carbon? I mean, carbon for sure is part of many organic molecules and compounds. I mean, why aren't we trying to detect carbon? I mean, I see methane, I see sulfurs, and I see other.
I'm pretty sure carbon is actually in the list. I might have omitted it
okay. Well, I mean, I thought it would be one of the major ones.
There's a lot of interesting things people can actually infer from those observations. For instance, in solar system, not in solar system, suppose you have a planet and certain features in the spectrum are changing daily. So their period is much smaller than, say, the orbital period of the planet, and in a much smaller period, some spectral feature, some line in the spectrum, some color appears periodically. Then you can assume that whatever the source of it should be on the surface of the planet, and it could be vegetation or something. Say carbon, imagine you see it with a period of a few days, then you can assume, hey, on the surface there's some source of carbon. But in general, I think the emphasis is on oxygen and methane because they're in the atmosphere, as opposed to carbon maybe not necessarily being there or something. But it's a very actually interesting question. I'll have to think more about that. Also, by the way, I have a question to people here. What do you think are the motivations to search for life? Why do we even care? Apart from it being just interesting, are there other motivations?
There's no guy there. What did you say? Repeat?
I guess perspective to maybe see that the universe is a lot bigger than we know it and we're not the only ones in it.
Right.
I think that we also
may also learn where we come from.
No, we ultimately want to know where we come from. Like, if there's other life out there, maybe that can help, like, oh, we're just a random chance.
Okay, that's a great version. Thank you.
So we don't feel lonely.
So we don't feel lonely. Yeah. Well, Richard, you have the.
Part of it was the existential one, but also like we don't know what life is. So it would be interesting to find other cases of it to actually, because we just think we know what life is because we have this one situation.
Victor?
I think it's more frightening to not search and believe that we're actually alone in the universe. I think that's a lot more, much more frightening reality than if there's
Curiosity.
Interesting. Yeah, it's just that, I mean, all of those reasons are completely valid, and I feel like every researcher has their own reasons. One researcher I recently heard, he said that unless there is life on an exoplanet, I don't want to study it. So some people are like specifically about life, some people just want to study exoplanets. But I just want to recall one interesting statement from a physicist I heard once, that physics might be simple, mathematically at least, in its basic laws. So you go through many years of training, then you get to say that it's simple. So, but it might be simple, he said, but physicists are not. So physicists are humans, and everyone has their own motivations. And I just wanted to share some of the motivations of mine that make me interested in that field in particular, and some of the things I read in a book called The Impact of Discovering Life on Another Planet, which is a collection of essays from different philosophers and thinkers. So to my delight, I found that a lot of people are interested in the question that I'm interested in, which is, can another civilization have a different mathematics? This may sound very specific and kind of arcane. Why mathematics? Why not say, can a different civilization have a different biology or different chemistry? Well, the reason for this intense interest in this question is that mathematics forms the foundation of physics, and physics is in the foundation of all sciences. And if mathematics can be different, that means physics can be wrong, like entirely, completely wrong. It could be that we think that those theories mathematically are elegant and our theorems are absolutely convincing and they're forever, but then it turns out that maybe another brain could produce another mathematics, and maybe our theorems would be incomprehensible to them, and maybe our proofs are not proofs to them. So what would that imply? This is scientifically a crazy idea.
I'm not trying to be excessively fatalistic, but I mean, I think we would all agree in this room that if a colony of ants got together, no matter how hard they tried, they're not going to build a space shuttle. Okay. What if we're the colony of ants trying to figure this stuff out, and we just don't have the IQs ever to be able to even pinprick the surface of the iceberg because we just don't have the intelligence? It's just not possible.
I agree with that, but it's certainly a possibility. And in a sense, I don't want to go too pessimistic, but I'm also a pessimist. So,
You're Russian, so yes.
I'm also a pessimist about this, about many other things. And one of my favorite pessimistic statements is that if everything goes well, we get old and die. So, and if you think about it, by the end of the day, you still have to accept that everything we do is kind of useless, but you still have to try.
I think it's like a group of very intelligent people that already know a lot of stuff. And you know what you know, but you don't know what you don't know. And so we're very inquisitive by nature, so we want to find out, like, what is the unknown? And we want to know more. And I think that's what we try and strive to be. I mean, you don't go to university to learn less. You want to learn something that you don't know. And I think that's the way humans are by nature. We try and find out more information. I mean, you go on the internet, now it's an overload of information. And you don't know where to start. Just like today, I opened up a book and it's like 300 pages, but if I go on the internet, I mean, there are thousands and thousands of pages of overwhelming information. And it's like I want to learn more, and I'm reading, and we try and strive to find out more. And I think that's why we do that. We already know a lot of stuff on Earth. We know how life exists here. We know all the chemical processes. We know what makes up the organic compounds. We know a lot of the chemistry, the physics. We know a lot of that. We just don't know what exists outside of there. So that's why I think we try and like start to find out information that's outside of this world. I mean, that's my opinion about the human nature.
You touched on it that we know more about, as far as the oceans are concerned, topography. We know more about the surface of the moon than we do our own ocean. If we're out here trying to come up with stuff like this, it's like, it's kind of like a monkey trying to like, figure out where it's at. It's just, I believe strongly that we're so limited in our knowledge that we can't even fathom how much we don't know. And maybe we might not even be able to be capable of getting to that level of understanding these things.
It's worth trying though.
It's worth trying, even if we're taking
as
a billion years to do it.
It is. I mean, that's the reason why we're all here, aren't we?
Sure. Absolutely, it's worth trying, sure.
Thank you. That was.
I was reading this article in Popular Mechanics about how life could take another form of like silicon-based life. Like for instance, on Atip, since it's the atmosphere is mainly methane and nitrogen, and how it's so cold out there that methane could take a liquid form. Maybe in the liquid oceans of methane, that different molecules can form and create a silicon-based life, and maybe that's why it's a lot harder to detect it, because maybe it's just committing a completely different signature. You have signature that we don't recognize to be life. So maybe they could be even within our own solar system that we're completely oblivious since we actually send probes and we have sent that one probe.
Is why aren't we doing this? It's just people are trying to do the simple thing first and to do something we know more about, because whatever we can say about silicon-based life is a hypothesis, whereas what our life is what we know, right? So it's a general approach in all of science, I would say, to do the simple thing first, try the easy approach first, and try the economical approach first, and then go for something more complicated. But I'm sure people are thinking about it and maybe proposing it as the next step. Well, I was told that it's time to wrap up my talk. Thank you very much.
And her presentation is called Is It Aliens? Once again, thank you everybody for coming out. This was such an awesome night.
Hello everybody. Oh my god, this is so loud. Okay. So the first two presentations were kind of very serious and math-wise, but I thought I'd kind of have some fun with this and just talk about a lot of times that we have seen possible alien sources, and I'm going to explain why we look at them or why we are looking at them, and just some other alien theory. So the first event that I will be talking about is LGM1. In 1967, Jocelyn Bell Brina was in her second year of her PhD, and she was looking at the way that quasar light looks through a solar lens. And what she was looking at was the sun, so she built this radio telescope and pointed it at the sun. And the first data she received back, she saw this kind of scruff every 23 hours and 56 minutes. And she's like, okay, the sun doesn't orbit, it orbits every 24 hours. So what she actually had seen was the stars behind the sun, which was a sidereal day. So she advanced her radio and took another set of data, and what she ended up getting was this plot right here, and she saw these evenly spaced pulses, exactly 1.337 seconds apart. These are actually bright, not dim. As I mentioned, they're actually upside down, so they're very bright pulses, very precise. And they had never seen this before, so they were like, she showed her visor, and she was like, well, what are these? We have never seen this before in a star. What can we possibly do with this information? So she ended up naming it LGM1, which stands for Little Green Men, because they possibly thought, oh, this could possibly be aliens. So then they took another set of data in another region of the sky, and they ended up getting the exact same feedback with these evenly spaced pulses, and she concluded this can't be aliens, because why would they be communicating the same way from a different region of the sky? So what she had actually discovered were pulsars, and what we know about pulsars now are that they are rapidly rotating neutron stars, and they have a very high magnetic field. This magnetic field is misaligned, and when it accelerates, it creates an electric field. and this electric field rips particles off the surface of the star and shoots them out at its poles. So when these poles pass in our field of view, we actually see these very bright pulses. And we know now that pulsars are very, very precise in their spin, more precise than a clock. So they actually, this is the very first discovery of pulsars. So there was a Nobel Prize awarded for this, but it sadly didn't go to her. It went to her advisor instead. So, yeah. So it wasn't aliens, sadly, but it was one of the very first events that caused a question of whether or not it was aliens. So the next event that I will be talking about is KIC 8462852, which is a very long name, but it's also known as Tabby Star and also known as the WTF star. It does not stand for what you think, it is what the flux, not what the, you know. So this was actually found during the Kepler mission, and this is, I believe, data from an F-type star. So if you look at the plot here, you can see these very strange dips. You have one here, another one here, and then they didn't really see anything for a while, and they're like, okay, that's kind of weird. And then here around 9, you see a very huge dip, and they're like, okay, what could that be? And then for a very long time, they didn't see anything until here, and you see this very, very strange dip. And they're like, okay, this is not something we've seen before from the star. So what could it be? After they collected this data, they published it, and well, the public got a hold of it, and they were like, oh my gosh, it is a Dyson sphere. And I'm pretty sure Richard mentioned a Dyson sphere earlier, but again, a Dyson sphere basically is a big alien structure around a star, meant to capture the energy of the star for use on a planet. And the idea was that this star was in a Dyson sphere, and the reason why there were very strange dips in the light curve was because it was coming through the structure of that Dyson sphere and the building. But sadly, they kind of looked further into it and realized, oh, it could just be dust from the star. We don't actually believe that it could be a Dyson sphere. So that was another sad conclusion that it wasn't aliens. But the next event I will be talking about are FRB and FRB repeaters. So FRB stands for fast radio bursts. They are extragalactic, which means they do come from outside of our galaxy. And they are very large broadband signals. So if you have a signal at 16 centimeters and you move it to 17 centimeters, you will still see it. And this also means that they are not man-made, because man-made signals are very narrowband. And all the FRBs that we've observed currently are from different frequencies. There have been a few repeaters, but it has been very rare. So a few theories have come out as to where those signals have come from. There are the astronomy-related theories, whether they come from black holes or rapidly rotating neutron star, gamma ray bursts, or binary white dwarf mergers. And then there are those that are not astronomy-related, which is the topic of today, which is extraterrestrial intelligence. So the first theory is that this is actually an alien airport. This bursts are coming from an alien airport. This is actually theorized by a Harvard professor named Abraham Loeb. I think I'm pronouncing that right. And he said that it is something very similar to a project we're actually doing here on Earth called the Breakthrough Starship Project, which is a plan to reach our nearest neighbor, Alpha Centauri, in a reasonable amount of time. So what this project is planning to do is put up this light sail, in our case named Starship, near the atmosphere of the Earth and shoot a bunch of lasers at it. And these lasers would actually be able to accelerate it up to the quarter of the speed of light. So our Alpha Centauri is actually 16 light years away. It would actually reduce the time down to 4 years away. So so he proposed that this could be an alien airport, but to actually do something like that, you would actually need a laser the size 2 times the size of Earth. So I don't really think that's happening, but you never know, because they could be more intelligent than us and could actually produce something like that. But the next object I will be talking about is Oumuamua. This is a Hawaiian name. I don't really know what it means. But this object was viewed October 19th, 2017 by the Pan-STARRS survey. It was the first interstellar object in our solar system. So this object did come from outside of our solar system, and if you see here, it's curved. It gets really close to the sun, and then it just keeps moving away, which is really weird. Because when this object was analyzed, they saw that it had a very, very fast speed, which isn't really natural. And the fact that it got very close to our sun means that it is not something from our solar system. So the question, is it a comet, is it an asteroid? And if you look at its spin, it is kind of tumbling. So they're like, oh, it could be a comet, but it didn't have a comet tail, so that kind of ruled it out. And then they asked, is it a piece of an alien ship that crashed and just entered our solar system? So, again, they kind of thought it was a solar sail, what I previously mentioned, because of its tumbling pattern that you can see here. But what they actually found is that it is venting gas that was heated by the sun. It's kind of like an intergalactic space fart. So it's just throwing out gas, and that's the reason why it is spinning and moving so fast. And they concluded that it does have a natural origin, but they're not completely sure what it exactly is yet. The next event I will talk about is the WOW signal. This was a signal that was observed in 1973 by the SETI, the Search for Extraterrestrial Intelligence, at Big Ear at Ohio State. So that is a picture of the radio telescope. As you can see, it's very big, but it's on the ground. So it doesn't have a lot of movement into where it can see. So it uses the Earth's rotation to view parts of the sky, and it can only look for 72 seconds. So on August 15th of 1977, researchers got this data back, and there wasn't live data analysis back then, so they actually had to print the data on paper. And the next, after a few days, they had some volunteers come in and look at the data, and they went, wow, what is this? Because as you can't probably tell by the code, but if you look here at the profile, you can see that this is a very bright object, like extremely, extremely bright, and they're wondering, where did this come from? It was not observed by the Very Large Array, which is another very big radio telescope, and it was never observed again. So there is still no answer to where this signal came from, so it is the biggest candidate currently for possible alien transmission so far. And you're asking, well, why do we look at signals that are radio-based? So if we look at the universe's spectrum, we have the cosmic microwave background and then the galactic background. But if you look here, there is a dip, and that dip is around the 21 centimeter spin flip line, which is a good tracer for baryonic matter, and we use it a lot in astronomy. That is actually a line that people cannot mess with, I guess. But if you look here, you can see that we have hydrogen and we have hydroxyl, and when you add those together, you actually get H2O, which is water. And if you think about water and holes, it's a water hole, and if you have water holes on Earth, typically different species gather around water holes, so that is why we think that aliens could possibly gather around this area, just kind of an idea. And then we have the Fermi Paradox, which Richard mentioned earlier. So Fermi, again, walked up to a bunch of his colleagues and asked, where are they? They meaning aliens. And they started working on a bunch of equations and a bunch of possible answers. And he went home and wrote a paper on what he thought. And basically he said, there are billions of sun-like stars just in our galaxy. Of those stars, some will have Earth analogs, which is probably true. Of those analog, some of them might have life, and of those that have had life, some of those might have done interstellar travel. So basically he's saying of the possibilities of interstellar travel and life out there, why haven't we seen anything? Because we should have. So there are a few theories and answers to his question that people have proposed. The first one is the Drake equation, which was mentioned by Richard earlier. So we have this equation that was proposed by Dr. Frank Drake in 1961, and it basically answers, it can prove that there is a big possibility or no possibility at all. So I kind of made up some random numbers I thought would plug in just to see how this would work. So the first part of this equation is the average rate of star formation per year in our galaxy. I said there are about 400 billion stars created in our galaxy per year, okay? The next question is the fraction of the stars with planets. I said, okay, let's say there's about a fourth of those that actually have planets in them. The next part is the fraction of those stars with planets. The average number of those planets that have developed an ecosystem. In our solar system, we know of one currently, but there may be another, so just to have a good average, let's say 2. Oh, sorry, that equals 100 billion, but then 2, and then you get 200 billion. And then we ask, what is the fraction of those planets that have succeeded in developing life? We'll say, okay, half of those, which gives us back to 100 billion. And then the fraction of those planets which have developed intelligence, we'll say, okay, a tenth of those. And then the fraction of those planets with intelligence that have developed interstellar communication, we'll say another tenth of those. So if you multiply all this together, it's about 1% of 100 billion, which gives you a billion. And finally, the last part of this equation is the average length of time such as a civilization would survive. We'll say 100 millionth of a possibility. And if we add those up, we get around 10 other possible civilizations in our galaxy that we could communicate with. But like Richard mentioned earlier, this equation isn't very good, I guess, because you could just plug in any other numbers. So let's say I change 100 millionth of the possible communications to 1/100. That would change around 10 possible communications to millions of possible communications out there. But then let's say again, what if there are no planets that could possibly live long enough to develop such communication? Then that would give us no possible communications. So this equation isn't that great because we don't, like Richard mentioned earlier, we don't know a lot of these for sure. So the next answer to Fermi's paradox was the rare Earth theory, which basically just says Earth is more rare than we thought. We could be just one of the special possibilities that we're so unique, and it's kind of self-explanatory. It's a rare Earth theory. But another answer to Fermi's paradox was the zoo hypothesis. So aliens know we're here, they're just ignoring us. Reasons could be we're not worthy, they want us to develop naturally, space policy, who knows. Maybe they just think we're stupid, which we probably are. But I leave you with this question, is do you believe in aliens? Thank you. I'm not sure if there's any questions. Mine wasn't that serious, but it was just a bunch of stories. Yes?
Is there a signal to detect wormholes? Because I know that Einstein theorized wormholes could exist, but is there some signal, a radio, some kind of that could lead to that?
I don't know. Personally, I don't know if Richard may know.
You mentioned it, the FRBs.
Oh, they're FRBs. Well, right.
These bright flashes of radiation that we see all over the place, that has no known origin, I mean, maybe.
That could be.
Right, because we don't know what FRBs are coming from. So it could be that, but we just aren't smart enough to realize that. So.
I know there was a detection for gravitational waves, like current or recent, that they were measuring gravitational waves of two stars going around in a circle or something like that. Is that possibly some way that we can also, some sort of communication, some other ways of communication between two civilizations, or?
Do you mean using the instrument that they use, or do you mean the gravitational waves themselves?
Gravitational waves themselves. Is that?
I don't think so. Just
manipulation of gravity.
Right. I mean, because gravitational waves are caused by the two bodies' masses pulling each other towards each other. I don't think it'd be caused by like an alien, like, oh, get together, maybe we send a signal, but you never know. I mean, yes.
I don't have a wordy scientific question here, but I wanted to ask anyone in the crowd. I was in the island like a year or two ago, and I looked up into the sky. It was at night, and I looked up into the sky, and I saw what I can only narrate as what was looking like dancing stars. And I don't know if anyone has any inquiry about
Dancing, you mean like
they
around
were-
each other, or?
They were like moving together, and so I stayed there for hours looking at this until I just decided to leave. And it was too far and to be anything. I was trying to find some explanation in regards towards this.
Were they fast?
See, it was too fast to be too far because they were moving, and then it was like trying to cross out everything that could be in the sky, and then for that long, and I was just like wondering if that's something you've seen through your research or like through like stories that you concluded through.
I mean, I know a lot of people see satellites and they'll be like, oh, what is that? But it's just a satellite. And they're really bright, actually, but two objects together.
It was in the same area for like 3 hours, and it was emitting light in a spherical manner, because you're able to, when I saw it, like, I was able to see it, both of them, and they would be like syncing together while they moved, and then they would branch off differently, and then come back in synchronization. And I was just like there, like, okay, do you see that? My friend.
I mean, I don't have like. I haven't seen that before personally. I don't know if anybody here has seen that before.
I mean, you see what you see. That's the thing. So it was real in the sense that you saw it.
Yeah.
With it, you're saying that there's these spots that were kind of like.
They looked exactly like stars, but then I saw them emitting, like, you can see that there was some spherical like shape that it was emitting like an angle, and so it might have been like, you know, if it moved, you can see it emitting different like maybe there was some type of edges or grooves that emitted the light differently at the angle.
Was it a windy night?
No, I remember there being a lot of mosquitoes after that.
Where are you?
No.
Like what part of the town?
I was all at the end of the road of South Park Island.
Oh, so there's quite. I saw the same thing before. It probably was there's blimps that I don't know this, but Border Patrol has blimps.
Okay.
And like they fly, they had these
That's what someone was telling me. But I'm like,
and they're super weird. Like I'm talking about stationary. Like it was right over SpaceX one time. I was on the island and we were looking over and I was like, holy crap, there's aliens over SpaceX, but it wasn't. It was a Border Patrol blimp, and like they were. I guess they're looking over Mexico with like their spotlights.
like it wouldn't. The way that they were moving. It's a great explanation that the way that they were moving. First, there's two. One was a little lighter, and one was a little darker. As far as the light being emitted, like it was a lot brighter, and they were in a sync. Like they looked like as if they were like doing the waltz. Like that's how I envisioned it for a long time.
Did they stay in the same spot in the sky, or did they move around throughout the sky?
No, it was just looking west. It was looking west up there.
If it was humid, there's a lot of mosquitoes and Victor brought this up too. We see this a lot in our research when there's a lot of water in the atmosphere and there's some sort of perturbation like wind. That's why stars twinkle, by the way. Stars don't actually twinkle, it's just because the air is moving. So if it's a particularly windy night or if it's very humid, the humidity thickens the atmosphere in a sense. And so whenever there's a slight change in motion of the atmosphere, you're going to see an apparent change in position of the star. If you saw them moving in the same way, it's probably because there was some current of wind in the upper atmosphere that shifted the light. You will measure it as an apparent shift. It's called an aberration in astronomy. So you might have seen some aberration. That could have been. I'm not saying definitively that, but of course. No, of course. Likely it's that. Yeah. It's great to see. Are aliens not? God, yeah.
Aim them out, put them down.
Interesting, Jack. Are there any other questions for anybody else? Ian, for you about that?
Do you know if 5G, right, has any effect or any adverse or negative effect now that we're going to start looking more at stars and stuff? Do those waves, frequencies, right, affect our satellites somehow? Or would they affect our satellites somehow? And how do, because I know that we look up at the stars at night to try to mitigate, the cities or, all the stuff going on, but would that affect somehow?
Do you, like
5G
instrumental wise or like us?
No, instrumental wise. Not us with our telescopes.
I think they would. I know there's been a lot of talk about that recently, that people are against 5G. So I would think that it is a possibility that it could affect how much we see.
Like interference, something like that?
Right, like interference, because just like how light interferes a telescope, even the smallest amount of it, I think the waves from 5G could interfere a sensitive enough machine.
Especially like a radio telescope.
Right.
I mean, these things, they can detect a microwave several football fields away. So they're sensitive to little things like that.
Yeah. Hopefully it doesn't take away our ability to detect aliens, right?
Right. And like a bunch of these are radio based, so that could be a big problem, but who knows, maybe we'll find another way to detect new things, just like the gravitational wave detectors are new. We can possibly do those things.
Yeah.
I think that's it.
Well, thank you all again for coming to the first official Stars on Tap event, and it will happen again, maybe not here, maybe somewhere else, but maybe, hopefully here, because this was awesome. So thank you all again for being a part of something really cool.